Hello, my name is Caleb Hires, and this is the white-throated sparrow. Specifically, this is a male sparrow, and he is likely singing to attract a mate or to defend his territory from other males. He was not born with the ability to sing this song. Just like a human learning to speak, he had to learn his song from older birds soon after he left the nest. Birdsong is, for the most part, a cultural trait, which means it's passed down through generations by learning rather than genetic inheritance. This means birdsong can evolve a lot faster than other traits that are hard-coded into DNA. Individual males in a population might start to sing a new version of their song, even if the genetic code has not changed. This might be what we're currently seeing in white-throated sparrows. A recent study found that the sparrow's song is evolving rapidly across North America. Originally, the sparrow sang what we call the triplet variant, which ends in a series of triplets that each contain 3 notes. However, sometime after the 1960s, a new doublet variant arose in Western Canada. This variant ends in a series of doublets that each contain 2 notes. The study found that the doublet variant has been sweeping eastward across the continent in the decades since, almost completely replacing the triplet variant. Biologists rarely see cultural evolution this rapid and this drastic. So, my research lab set out to document the shift from triplet to doublet in the Springfield area. We soon came across a problem. When attempting to label songs as doublet or triplet, there was a lot of disagreement. Sometimes a song would sound like a triplet to one person, but a doublet to somebody else. Other songs had irregular rhythms that didn't quite fit into either category. This is problematic because we can't figure out how the sparrow's song is evolving if we can't even agree on how to score an individual song. Therefore, the focus of our study is to create a new computational method for scoring sparrow songs as doublet or triplet. In doing so, we hope to eliminate observer bias and enable more accurate analysis of the song's evolution. Now, I won't get too deep into the details of the algorithm, but the main idea is that the computer scores songs by measuring the time interval between the start of each note. Here you can see the final notes of the doublet variant song and the final notes of a triplet variant song. I've marked the intervals between the beginning of each note. If you look at the intervals in the doublet variant, you might notice a pattern. The average A interval is relatively long, while the average B interval is relatively short. Therefore, if you divided average length of A by average length of B, you get a pretty high number. Now look at the triplet song. You'll notice it does not follow the same pattern. Some of the A intervals are short, but others are long. The same goes for the B intervals. So if you divided average length of A by average length of B, you get a low number somewhere close to 1 because the two averages are relatively similar to each other. This is how our method assigns a numerical score to song recordings. A higher score means a song has a more doublety rhythm, while a lower score means a song has a more triplety rhythm. Just as we expected, this method scores songs a lot more consistently than individual humans. It also gives numerical scores to songs with ambiguous or irregular rhythms, meaning we can now describe variation in song rhythms beyond the doublet-triplet dichotomy. We hope that our new method will allow researchers to tease out which part of the sparrow's songs are actually evolving, how quickly they are evolving, and eventually why they are evolving. So next time you hear a white-throated sparrow song, know that you're witnessing a cultural phenomenon we're only just beginning to understand.